are live on the internet. Okay, let's go. 1, 2, 3, all eyes on me. Oh, I didn't hear that one before. Let's count and walk straight. That's funny. Oh, did you really? That's something you would say to like a kindergarten or first grade class. They have a hard time working straight. Do you ever watch a group of first graders? They are squirrely goofballs. I mean, it's like, it's crazy. Okay, I got a review problem for you. I think so. Yeah. Can you find me the tangent line when x equals 0?
Oh my goodness. Oh, yes, I can.
Let's see it. Go for it. You need a piece of paper, Jeff? Here's some paper. Or can you do that in your head? You're trying? In case you need a piece of paper, here you go. There's a pencil in case you don't have one of those either. Huh? No? Oops, F, oops. Ah. Okay. So you have to get the point of tangency, and you got to get the slope at that point. And so I get the point of tangency is 0, 1, and I get the slope is 1. And so my line is y equals x plus 1. Okay. You never understood what? Yeah, let's graph this and take a look at it. All right, let's get a better grasp on that. Come on, GeoGebra. Didn't I just hit new window? Come on.
I can just eat popcorn all the time.
Oh, there we go. Okay, so here's my new window. Let's blow up the font. So if you have a calculator, graph these two functions together. Font size 24. So I'm going to graph e raised to the x. I'm going to graph y equals x plus 1. And don't they look nice? They mimic each other. Okay, now that's a tangent line. If I just kind of block part of the screen here, like if I hide that, that looks kind of like a parabola, doesn't it? Kind of, sort of. Wouldn't it be cool instead of finding a tangent line, finding a tangent parabola? Because here's the cool thing about a line is nice, it's easy to work with, but a parabola has concavity. Doesn't this curve have concavity? Is it concave up or concave down?
Concave. Oh, what? It looks like a sad face. It's concave up.
It is concave up. Looks like a sad face, really?
No, it looks like a happy face.
Looks smiley to me. Okay, so that is concave up. So what I want to do is I want to try and find a parabola that is concave up, that has the same tangent line at that point. That's my goal right now.
This is not really review. This is fake.
No, this is totally review. What do you mean? You know how to do concavity, right? You know how to do tangent lines. This is totally review. Okay. The question is, what the hell does this have to do with series? That's the real question. We're getting there.
Oh my gosh, hey, I've never been able to do one with that many.
Tangent parabola.
Oh my goodness. This is algebra.
Okay. So we're going to try and find the tangent parabola. Now, here's what we need to have happen. We want them to have the same tangent line and the same concavity. Well, how do you determine concavity?
You see if it's a smiley face or a sad face.
Okay, how do you determine concavity with calculus?
So you find the zeros
Of what?
of the tangent line? No, of the when you
Anna?
equals what x equals.
A table, and what do you do? What do you do with that table? Like, do you use the first derivative maybe?
Yeah.
Or the second derivative? Okay, second derivative tells us about concavity. It tells us how the slope changes. Okay, so let me just explain that part, and then we'll do this. So if I were to go back to this picture here and just hide these suckers for a moment, and we take, why didn't you hide? There you go. There you go. Okay. So I'm going to graph just y equals x squared. And then I'm going to stick a point on it. Boom, point. And then I'm going to stick a tangent line on that. Boom, boom. Okay, so there's the tangent line. Okay. Now the cool thing is, now would you say this tangent line has a negative slope?
Yeah.
Okay. And if I grab A and move it, is the slope still negative of the tangent line?
Yes.
Yeah. Slope still negative?
No.
Yeah. It's still negative. It's still negative. Still negative. Okay. So let's adjust the screen on the side here, move that down. Where's my tangent line?
Which is how you could draw it.
Oh, let's get the slope of this line. GeoGebra has a slope tool somewhere. Slope. Okay, click. Okay, so the slope, let's put that in a more convenient place. It's not letting me move it. Can you see the slope's negative 0.41? Okay. All right. Over here, come on, point. There we go. Over here, the slope is like negative 2, negative 1-ish. Okay. And then all of a sudden it becomes 0 and then positive. So my slope is doing something right here, and I believe as I drag the point from left to right, my slope is increasing. Right? It goes from negative 2 to negative 1 to 0 to 1 to 2. That's an increasing list of slopes. Right? Slopes are increasing. Slope is the first derivative. My first derivative is increasing. In calculus, we determine if something is increasing or decreasing by taking its derivative and checking the sign.
Yes.
Right? So if I take the second derivative, and the second derivative is positive, that means the first derivative is increasing, which means the slopes are increasing positively. And if your slopes are increasing positively, you have a smiley face. If you have a smiley face, it is concave up. Okay? So if we take the rate of change of the slope function, which is the derivative of the derivative, that's why it tells us concavity. That's the geometry behind it. Okay. Anyway. So we need to find the second derivative of this guy here. Well, y prime is equal to what? 2ax plus b? Right. And y double prime would be, hey, 2a, that's nice. Okay. Now, we want the exponential function to have the same concavity when x is 0. So we need to find the second derivative of our e to the x function. So let's see. F prime of x is what for e to the x? Okay, excellent. This is getting a little harder. What's f double prime? E to the, okay, it wasn't that hard. E to the x. All right. Now what's the x value we're picking on here? X equals 0. So we need to now know what is f double prime of 0. Okay. So that means we want the derivative of the second derivative of this parabola to be exactly 1 also. Can I now figure out what a is? Yeah. A must be 1/2. Okay. Can I figure out what b is?
Yeah, because you can plug it into the normal derivative.
Yeah.
Oh,
so, well, what's the first derivative evaluated at 0? F prime of 0 is 1. So that means we want this to equal 1 also. Okay, what's x here? 0. So that gives me 2a times 0? So the only thing that matters is b, and what's b here? So we just figured out that a is 1/2, b is 1, c. C is the y-intercept. That has to be the y-intercept of e to the x. What's e to the 0? 1. We now know if we have a parabola with the coefficients 1/2, 1, and 1, it should have the same tangent line and have the same concavity as e to the x at the point 0, 1. Let's graph it and see. Isn't this exciting?
I like that it's algebra.
All right, where's my calculator? Here we go. And let's make that go away, and that go away, and that go away. And we want this back. All right, what's my parabola again? It's what, 1/2 times x squared plus 1x plus 1. Now check this out. If I ignore the 1/2 x squared, I have just x plus 1.
Hey, that's the e to the x thing.
That's the tangent line. The tangent line is hiding in the tangent parabola. Is that a coincidence, maybe? Maybe.
Probably not.
Maybe not. Let's see. Let's graph it and see if it looks good. Oops, what happened? X plus 1, if I ignore the squared term, is my tangent line.
Which is mind-blowing.
Is it a coincidence that the tangent line is living within the tangent parabola?
And that's really cool.
Enter. Ooh, look at that. If I zoom in, that parabola very closely matches. If I put the tangent line there too, check out the tangent line. The tangent line's a good match, but isn't the tangent parabola a tighter fit?
Yeah.
Isn't that incredible? I mean, you zoom in far enough, you can't tell the difference. Let's turn off the tangent line. Look at that. Okay. What's so special about a parabola? A lot. But hey, why not do a cubic?
What? I'm not ready for that. This is too mind-blowing right now.
Okay, next step. We're going for tangent cubic.
What?
Yep.
Okay, that was really loud. Sorry.
Okay. So, because that's the third derivative, right? Is what's going to come into play next.
Yeah.
Yeah, so the third derivative is the rate of change of the concavity.
Okay. This might take some time.
And I don't know geometrically what you call that, but physically, does anybody know what the third derivative is?
Oh, isn't it a jerk?
It's jerk.
Oh, yeah.
Yes, it would snap your head back. It's jerk. Okay, so we're going to figure out the jerk for e to the x. Okay, so now we are going for y equals, let's see, I need another letter. I guess I'll call it a sub 3 x cubed plus a sub 2 x squared, a sub 1 x plus a sub 0. This is my tangent cubic.
Cubic.
I'm going for a tangent cubic. All right, to do that, I need multiple derivatives. I need to get down to the third derivative here. First derivative, y prime. 3, a sub 3 x squared, right? Instead of, because I called the others like a, b, and c, I guess I could have called that d, but then the letters were out of order and that was freaking me out. But the d would be out of order and it doesn't match the other letters, and right? Because before, didn't we write down a, b, c for the letters? I felt weird putting D in front of A. I am not going to do that. All right, so those guys are going away. This is what I'm doing. We're using subscripts. We can do subscripts, right?
Yeah.
Sequences are subscripted, aren't they?
Yeah.
Okay, we can handle it. All right, subscripting. So what's this? 2a2x plus a1? All right, next, y double prime. 2 times 3. Oh, interesting. Or 3 times 2, maybe. A3x plus 2a2. Because I like 3 times 2. It reminds me of something. And that's really an x to the first, isn't it? Yeah, it is. Y triple prime. What do I bring down the power and multiply? Is that right? So that's going to give me 3 times 2 times 1 times a sub 3. What's so nice about writing 3 times 2 times 1? It looks like 3 factorial. Holy shit, it does. This looks like 3 factorial times a sub 3. Okay, that's kind of cute. All right.
Oh my goodness, are we going to figure
Yes. Yeah. All right. We need to find f triple prime of x. What's the third derivative of e to the x? It's still e to the x. Okay, that's no work. That's good. And we have to then evaluate that at 0, which is, so that means this 6a sub 3 has to be equal to 1. So a sub 3 has to be equal to 1/6. Or if you prefer, 1 over 3 factorial. Okay. So you might think, I'm just writing down factorials because I like them, which is partially true. Well, I mean, I do like them, but that's not the only reason I'm writing them down. There's another reason behind that. All right, so now here's the deal, though. What x value are we plugging in to check all this stuff? 0, right? And if I plug in 0 to go back and test the second derivative for a coefficient, if I plug in x equals 0, that term's gone. And the second derivative evaluated at 0 is 1. So what's a sub 2 have to be? The same as it was before. Wasn't this coefficient 1/2 before? It still is.
Oh my goodness, and then the rest?
And here, if I plug in 0, these guys are gone. And what's the first derivative evaluated at 0? And wasn't this 1 before?
My mind just being blown.
Okay, so now we have a tangent cubic, I think. Let's check it. Okay, so we got to zoom back out. Is that the right way? No, that's the wrong way. I don't know. I felt the same way when I first learned this. This changed my life. All right, so I'm just going to modify g of x here by in front adding on that cubic term. So my cubic term, oops, I went too far, is 1 divided by 6 times x raised to the third plus all that other crap. Enter. You see anything change there? If I zoom out, you'll see a difference. So here's the cubic function, zipping along, but look how tight they sit in there. That's tighter than the square. Now, why stop there, though? We can just keep going.
Yes, we can.
We could go a 4th degree or a 5th degree.
Then you just do 1 over 4 factorial, 1 over 5 factorial.
Can't I just do it forever? We are discovering a power series for e to the x by looking at its derivatives. Right? Can you guess now? So check this out. There's a pattern evolving here. Let's look at the pattern. New page. N versus a sub n. Okay. So if n is 1, oops, we found our first coefficient was 1. When n is 2, we found our second coefficient was 1. No, because remember the tangent line was 1x plus 1? Yeah, when a was 3, oh, actually, no, shit. I'm right, I started with n equals 0. Right? 0? I forgot. I counted at 0. That matters. Okay, starting with n equals 0, then 1. Okay, a sub 2 is, Jeff, 1/2. Okay. A sub 3 looked like 1 over 3 factorial.
I know which it is, because then it's 4 factorial.
Yeah, because think about it. A tangent quartic would have an a sub 4 times x to the 4th, right? And if I take the first derivative, I get 4 a sub 4. You got it? You see what's happening? And then the 3 comes down, then the 2 comes down, then the 1 comes down. So what does the 4th coefficient have to be? What does the nth coefficient have to be? So we believe now, based on the derivatives of e to the n and the pattern we've observed, that e to the x is equal to 1 plus x squared over 2 plus x cubed over 3 plus ... x to the n over n factorial, and just keep going. We've just developed a pattern that says these guys ought to be equal. Now, this is a power series, isn't it? Yes. We found the radius of convergence of this. Anybody recall what it was? We applied the ratio test to this earlier in class. It's infinite. It's infinite. So if e to the x is really equal to this, it is so for all real numbers. How did we find this series, by the way? We used derivatives, right? Yeah. Okay, so we use derivatives to find coefficients. Derivatives. I just have one statement to write down, then I'll shut up. Derivatives to find coefficients. Oh shit, right. Yeah. Refactorial. I might have tried to write it, my pen refused, I'm not sure. Okay. The derivatives were used to find the coefficients. That's a special technique. It doesn't just work for e to the x, it works for a lot of functions. I like it. Okay. And even better than that, when you use derivatives, these power series get a special name. They're called Taylor series or Maclaurin series. I'm going to call it Taylor series for now. Because two mathematicians, Taylor and Maclaurin, discovered this connection between derivatives and power series back around the time of Newton, or maybe a little after Newton. Taylor was British or English. Maclaurin was Scottish, I think. And I don't know if Britain and England and Scotland were getting along then, so it could be they were both working on the same stuff at a similar time, but really couldn't communicate because of some. I used to know the history. I can't remember right now, but yeah. So I'm going to call this one a Taylor series. So Taylor series is a special kind of power series where the coefficients are derived by repeated derivatives. Okay. So. Wow, that was a lot. All right, so you guys got a lot of homework to work on. This is 10.8. This thing I did right here is 10.8. We have a lot more work to do in 10.8. We just scratched the surface. 10.7, what was we doing in the beginning? Correct. Get 10.7 down first, then worry about 10.8. Okay. You should definitely start 10.8 and look at it in the book. And you should do your very best to finish 10.7 and hit that wonderful button if you get stuck. What button is that, Anna? Ask your instructor button. Yes, please use that button.